Hello, AP Physics 1 students. If you haven't already, go ahead and read problem number 7 and get a bit of a start on it. There's basically two main ways to go about solving this problem, so see what you are doing and then come back to the video to see how I set it up. Okay, so I'm going to go through two major ways to solve part A here. So I've got the dividing line here, and so as I start to go through a solution, if it's not the one that you did, well, maybe in your notes or somewhere else, you maybe want to copy down other ways to do it and go back later and try it again on your own in a different method. So one way is from a torques approach. So you start with sigma tau equals I alpha, which of course we rearrange to alpha equals sigma tau over I. In which case we have to find the net torque. Right? So there's two torques here. There's Bob pulling on it, trying to speed up the wheel, but of course there's also a frictional torque opposing the motion, and so of course we're going to have a negative sign there for the torque from friction. The other way to go about it is using the work-energy theorem. Now, really W net equals a change in rotational kinetic energy plus a change in translational kinetic energy, but it's only rotating, right? It's not like the wheel is coming off of its axle and rolling away. That would be very, very dangerous. You saw the video, right? It's a huge, huge wheel. And so it's just rotating on its axis, so it's only a change in rotational kinetic energy. Net work, in a rotational sense, of course, is sigma tau times delta theta, and we can split up the rotational kinetic energy change into final minus initial. The wheel starts from rest, so really the initial rotational kinetic energy is going to be 0. Again, sigma tau is going to be the difference in the torques, the torque from Bob's pull, RF sine theta, minus the frictional torque. And we can replace rotational kinetic energy with its equation, 1/2 I omega squared. Again, we're only going to look at the final kinetic energy because it starts from rest, just like we saw in the video. Through either method, you're going to have to find the moment of inertia. So at this point, depending on which one you went through, maybe pause the video, calculate the moment of inertia. It does say it's a solid cylinder, so we're going to use our equation for 1/2 mr squared. Notice, though, you're not given the radius, right? You're given the diameter. So we should be getting 79 kilogram meters squared, which you're going to use in either of these methods, either using the torques approach or the net work approach. So at this point, if you haven't solved it yet, maybe pause the video, get as far as you can in letter A, and come back to see the solution. So for finding alpha, the radius is the 1.1 meters, and that's how far away Bob is pulling on the wheel from the center of rotation. I'm saying that theta is 90 degrees. Now let's be very, very careful here. This is the theta in RF sine theta for torque. That's not the same thing as delta theta, which I know can be very, very confusing, right? Remember, the theta here is the angle between the position vector and the force being applied. And so it says he's pulling tangent to the wheel. The position vector is basically the radius of the wheel, and of course they're going to be at 90 degrees to each other. Sine 90 is 1, so I'm just dropping that out immediately just to remove the confusion. And so here as a checkpoint, you should be getting angular acceleration of 3.9 radians per second squared. And then you can just use a kinematics equation. I like to use the time-independent kinematics equation to find the final angular speed. But here's delta theta. Now remember, this delta theta is not the theta in the torque equation. This is the actual angular displacement, which is given as 45 degrees. But we know we can't use degrees. So you have to convert. So if you didn't do that, go ahead and convert. You should be getting delta theta as 0.79 radians, and then when you put it all together, you should be getting the angular speed of 2.5 radians per second. Going to the other method, if we rearrange this equation for the final, it's going to look like this. Once again, when you put your numbers in, we can't use delta theta in degrees, so make sure you have the conversion done. Once again, the theta in RF sine theta is 90 degrees. I know it's very confusing, the previous step there. Both thetas are there playing completely different roles in the equation. But it's 90 degrees, times 90 is 1, it drops out. And so either way, you should be getting the final answer of 2.5 radians per second when you round it to 2 sig figs. I go on to letter B, where again, there are two main ways of going about it. And so maybe if you did the torques approach the first time, maybe you want to try the energy approach this time, or if you did the energy approach the first time, maybe you want to try the torques approach this time. Or you want to stick with it, that's fine as well. I'll show the setup for both. So in B, part 1, we're trying to find the number of revolutions it completes. We've seen this before back when we did rotational motion. Number of revolutions is really a measure of delta theta. So our end goal is to find the angular displacement it goes through. From the torques approach, you do sigma tau equals I alpha, so alpha equals sigma tau over I. You can find the angular acceleration from that. From the work and energy approach, you go right back to what we've done before, the network equals change in rotational kinetic energy. And so just solving that for delta theta, notice that it's negative I omega squared over 2, which is really negative 1/2 I omega squared, because it started with some kinetic energy and it's coming to rest. You know, the final rotational kinetic energy is going to be 0. I just put the 2 in the denominator just to make it look a little fancier. I don't know, I like it that way. Either way, though, we're doing sigma tau. And so you have to realize once Bob lets go, what's the only torque applied to the wheel? It's going to be the frictional torque. And since it's opposing motion, don't forget that's going to be negative net torque. Just to give you a heads up for the next part then, of course, if you're doing the alpha approach, you're going to have to use a kinematics equation. So I like the time-independent kinematics equation, although certainly you can go out of order. You can find the time it takes to stop first and work backwards. There's all sorts of orders you can go about to solve this problem. Of course, omega final is going to be 0. We have the initial speed from before. And to give you a bit of a checkpoint, alpha here is going to be negative 0.44 radians per second squared. You should be expecting a negative angular acceleration, because of course it's slowing down. Through either approach, you're going to find delta theta at 7.1 radians, which of course is not the answer, because our answer has to be in revolutions. And then it's just a matter of doing a unit conversion. We convert it using 1 revolution for 2 pi radians, you should be getting the 1.1 revolutions. For the last part, taking the time it takes to stop, we'll just pick your favorite rotational kinematics equation, or perhaps you went out of order, you found this time first and worked backwards. Either way, here's a couple ones that you may want to use. You know, my favorite one is delta theta equals omega bar t, so solve that for t. Or, of course, you can use the angular acceleration equation. Either one should get you the time of 5.6 seconds.